Okay, this lecture we will introduce some special functions, gamma functions, and later on probably we will introduce Riemann zeta functions. Those special functions are originally already defined for real numbers, but now with the help of the complex analysis, we can extend the definition to the whole complex plane as a meromorphic functions. Okay. With the extension, we can prove a lot of fantastic properties later. So this is first topic. The second topic is we will finish up the discussion of residual theorem and the calculation of integral by one more type of problems, that is summation of discrete values. Okay, so we start with special functions. So recall the following gamma function. Probably you already know this from calculus 3 or math 522. It's defined to be integration from 0 to infinity tx minus 1 exponential negative t dt. And here x is a positive real number. By the integration by part, we can have the following recursion relation. Integrate by parts. For x greater than 1, I will explain why we have this restriction on the variable x. Integration by parts gives you this and plus x minus 1 times integration 0 to infinity tx minus 2 exponential negative t dt. And if you plug in infinity, you have 0. When you plug in 0, because x is positive, x is greater than 1 strictly, so this is 0. And then you know that this is x minus 1 times gamma x minus 1. Immediately, consequence is, since gamma 1 is integration of e negative t, so this is 1, then gamma n is n minus 1 factorial. Okay, now let's look at why x, as our original definition, x should be positive, because for convergence. Because here, when t goes to infinity, because you have exponential decay, so this one is convergent at infinity. And but when x goes to 0, when t goes to 0, exponential negative t is close to 1, so it's a positive, bounded by a positive number. And then, so we should say when t goes to 0, tx minus 1 exponential negative, almost like t to x minus 1's power. So for this integral to be convergent by the p-test, definitely we need to have 1 minus x less than 1, which is same as x greater than 0. Okay, then next we want to we claim that gamma z defined by the integral, same integral but change x to z, So this is well defined for z in C, real part z greater than 0, and moreover, it is holomorphic in the corresponding domain. So proof, first, the definition should be understood in this way. Limit epsilon goes to 0 plus r goes to positive infinity, or the integration epsilon to r tz minus 1 exponential negative t dz. And first we show that the gamma z is well defined. In other words, we need to show the limit, the double limit exists. So for this, we noted that for the right hand side, this one is bounded by okay, so let's do it rigorously. So you cut this because you have two okay, let's do it rigorously. It suffices to show that the limit epsilon goes to 0 plus epsilon to 1, and the limit r goes to positive infinity integration 1 to r tz minus 1 exponential negative t dz exists. Okay, and then for the first one, the limit exists. We need to estimate the by the Cauchy criterion, we need to estimate this integral. It suffices to show that this integral goes to 0 as epsilon prime goes to 0 plus, and this integral goes to 0 as r prime goes to positive infinity. So this is by Cauchy criteria in Math 521. You need to estimate the tail. Okay, and then for the first one, because it's close to 0, so exponential negative t is bounded by 1. So this one will be so this will be bounded by for example 2 times t. So let's write, okay, let's step by step. This is integration epsilon to prime to epsilon exponential log t times real part z plus I imaginary part z minus 1 exponential negative t dz. So this is epsilon prime to epsilon exponential log t times real z minus 1 times exponential log t I imaginary z exponential log t dz. Okay, so for this part, the norm is 1. For third part, it's bounded by 1, and for this part, first factor, it's bounded by, so this will be less than or equal to integration for epsilon to prime to epsilon t real z minus 1 and dt. Sorry, here is dt. Yeah, I made a mistake. Those are t. My bad. The integration is with respect to t. Okay, now since real part z is greater than 0 by the assumption, so the integral, so this one you can just integrate it. This is 1 minus, so minus, so it's real part z times t real part z epsilon prime. So this goes to 0. So this goes to 0 as epsilon prime goes to 0 plus. Okay, similarly, let's look at the second one. So for second one, noted that the key part is planned by exponential negative t. So first noted that t z minus 1, the norm of this one is t real part z minus 1. Okay, no matter how large z is, this will be less than or equal to exponential r over 2 as r goes to positive infinite, as r larger enough. Therefore, without loss of generality, we can assume r prime is greater than r. So t z minus 1 e minus t dt, this will be less than or equal to integration r prime exponential negative t over 2 dt. So this goes to 0 as r prime goes to positive infinity. Okay. So we completed the first part, that gamma z exists for all the complex number lying with positive real part. Okay, next we want to show this is holomorphic. We will show that gamma z is holomorphic for z in C, real part z greater than 0. So to prove this, we take the derivative. So first noted that claim partial x z minus 1 exponential negative t dz equals integration 0 to infinity. So this you can write down as exponential log t x plus iy minus 1. So if you take derivative with respect to x, you have tz minus 1 exponential negative t and times log t dt. And similarly, when you take y derivative, of the integral, you expect to get I times log t, tz minus 1 exponential negative t dt. Okay. So proof. To establish this by a theorem in Math 522, we need to show that it suffices to show that log t z minus 1, t to z minus 1 times exponential negative t is absolutely integrable. So in other words, we need to prove exists, and for the second part, the same thing. Okay, and to show that, we just need to note that first integral is same as second integral. Therefore, we split the first one into two parts, 0 to 1 and 1 to infinity. And the integrand is just this one. Okay, then for the 0 to 1 part, noted that log t let me first write down it. Log t is less than t to negative real part z over 2 when t small enough. Therefore, this one will be bounded by some constant times integration 0 to 1 t real part z over 2 minus 1 exponential negative t also bounded, so can be reduced to this one. As we showed before, this is bounded. Okay. And then for the second part, it suffices to note that log t tz minus 1, the whole thing is bounded by exponential t over 2 times some constant dt. So the whole thing is bounded. Okay, then you can change the order of derivative and the and the integration. Actually, I think here you need one more condition, and continuous, and it's continuous. Yeah, for the continuous part, I think it's also easy, but you need to do some work. I leave it to you. Why continuous? You need to do the estimate. Notice that here we require the derivative. The integral of the derivative is continuous, not the original function. The original integral continuous. Okay. Then we can interchange the derivative and the integration. Okay, after that, we notice that actually, gamma z, we can show that gamma z is continuous. Okay, because you can think of gamma z y square higher order derivative. They are both continuous. So, not continuous, smooth. Then we can apply the Cauchy-Riemann operator. And then you plug in, you find it's 0. Therefore, gamma is holomorphic for the right half plane. Okay, so here the key point is you need to show that you can change the order of integration and the derivative. And I didn't show the the smoothness of gamma z, and this is also required if you want to apply the Cauchy-Riemann operator. Okay, anyhow, we show that. Next, we introduce the beta function. So we start with this definition of beta function, which is gamma x, gamma y, divided by gamma x plus y. Okay, but we still want to have some integral representation. Because when you do if you want to find some recursion relation addition formula, integral representation is better than the abstract definition by gamma x times gamma y divided by gamma x plus y. You have more room to manipulate. Okay, therefore we try to simplify this product gamma x times gamma y. To avoid the confusion, we use variable u for the second integral in place of t. Okay, and just to recall, gamma x plus y is integration t from 0 to infinity tx plus y minus 1 exponential negative t dt. Therefore, here, kind of you need to combine the index x and y, so that you might have a chance to produce gamma x plus y. And then we let u equals tv. And then the above formula can be written as the first integral is the same. For the second one, v is from 0 to infinity, and tv y minus 1 exponential negative tv times t dv. And you view this as double integral so that you can simplify it. Tx plus y minus 1 exponential negative 1 plus v times t, v from 0 infinity, vy minus 1 exponential negative tv dv. Okay, for the first part, recall that here you have minus 1 plus v times t as the index, but here you only have t. Then if you want to produce gamma x plus y, the index should be the same as the base of the power function. Therefore, we take omega to be t times 1 plus v. Okay, then if you plug in, you have t from 0 to infinity tx plus y minus 1 exponential so here you have dt, negative omega and d omega divided by 1 plus v. So here t also, we also need to replace t by omega over 1 plus v. Integration v from 0 to infinity, v y minus 1 exponential negative t. Sorry, you don't have this part anymore. The exponential part has been combined in the first integral. Okay, then you simplify, you have of course here it's omega. So integration from 0 to infinity omega x plus y minus 1 exponential negative omega d omega, and then you have v y minus 1 divided by what's next? It's divided by 1 plus v x times y dv. Therefore, note that this is exactly gamma x plus y. Therefore, beta is b. Bxy beta function is integration from 0 to infinity v y minus 1 plus v x plus y dv. This is integral representation, but not so appropriate to our purpose because x, y are not symmetric. But from the definition of beta function by gamma functions, it's clear it's symmetric. So this form doesn't manifest the symmetry. It's not a good one. So next, we let mu to be lambda divided by, v to be lambda divided by 1 minus lambda, and lambda is from 0 to 1. So it's clear when lambda goes from 0 to 1, v goes from 0 to infinity. So it's a monotonic function. V is 1 minus lambda minus 1. dv is 1 over 1 minus lambda squared d lambda. Okay, then beta function, beta xy, can be written as lambda from 0 to 1, lambda divided by 1 minus lambda, y minus 1, 1 minus lambda, x plus y, d lambda, 1 minus lambda squared. Simplified, it's integral from y minus 1 times 1 minus lambda, x minus 1, d lambda. Now it's clear, when you change x and y, beta function is the same. So this is a good representation of beta function, integral representation of beta function. Okay, and we will come back to this beta function later, but then we look at the gamma function again. So gamma function, recall that for gamma functions, we already defined on the right half plane, so gamma functions. A natural question is, can we extend the gamma function to left-hand side? In general, as we showed before, it's very hard to extend holomorphic functions. You always have weird singularities at certain boundaries, such that when you do some extension, you have trouble. Okay, but for all the special functions, I would like to say, they always have good extension properties. So the deeper reason is symmetry. So here, what is the symmetry? Look at the beta function, gamma x times gamma 1 minus x divided by gamma 1 is beta function. So is integral from 0 to 1, 1 over t, 1 minus x, 1 over 1 minus t, x, dt. Okay, since gamma 1 is 1, then what do we have? We have gamma x, gamma 1 minus x is integration of 1 over t 1 minus x times 1 minus t x dt. If you still cannot recognize it, let's change the variable t to x, x to alpha. So what do you have? That's the integral we studied last time. So we know the answer is pi sine pi x. Okay, so let's rewrite it. Gamma x, gamma 1 minus x is pi sine pi x. So what does that mean? That means you look at the arguments x and 1 minus x. They are symmetric around the line x equals 1/2. And therefore, no matter so we have gamma x is pi over sine pi x times 1 over gamma 1 minus x. So if x is less than 0, 1 minus x is greater than 1. So gamma 1 minus x is well defined. So kind of you can, no matter what value you have, on the positive real axis. From this number, you can define gamma x here. So this is 1 minus x. If you know gamma 1 minus x, you can define gamma x. Okay, especially around the line x equals 1/2. In this region, so on this real number line, the relation holds. Okay, think about this. It's very deep. If we have this is called a functional equation, which is the basic principle in analytical number theory, even in the nowadays very popular long-range program and the representation theory. The very basic stuff is called functional equation. As soon as you have function, also the integral representation is also very important. So the functional equation give you one way to extend your function, your holomorphic function, from this half to another half. The geometry is you just reflect. So the conclusion is, we will prove this conclusion just in a moment by reflecting the value, or just very loosely speaking, reflecting gamma z along x equals 1/2, we can extend gamma to the whole plane, complex plane. But of course, since if you use a functional equation, you know, gamma 1 minus x now is in the denominator. Also, you have sine pi x, so you cannot expect holomorphic functions, but at least you have meromorphic functions as a meromorphic function. So next is a lemma we are going to show. Define gamma z by integral when real part z is greater than 0, and we denote it by fz. And gamma z to be pi sine pi over z times 1 minus gamma 1 minus z, 1 over gamma 1 minus z, and if real part is less than 0, and z is different from negative integers. Actually here I think okay, so here we need to modify a little bit. It's less than 1/2. Okay, and then z is different from 0, -1, -2, -3. Then gamma z is well-defined meromorphic functions function on C with simple poles at z equals 0, -1, -2. Okay, so proof. So first, we need to, so we denote this as Fz, F2z. First, we need to show, it is clear that F1z is holomorphic for real z greater than 0. F2z is meromorphic for real part z less than 1/2. Okay, now to show gamma z is well defined, if we look at the picture, what do you need to do? You have F1 here and along x equals 1/2, you have F2 defined here. So to guarantee gamma z is well defined, of course here you miss a certain point also. On this point you have poles. Okay, then to guarantee gamma z is well defined, you need to show F1z equals F2z on the stripe. X is real part z greater than 0, less than 1/2. Just an overlap part. Okay, how to show this? In general, if you have smooth functions, then this is hard. But notice that those are real functions, and therefore it suffices to show that F1z equals F2z for z a real number between 0 and 1/2. Because we show by the uniqueness, meromorphic functions, actually holomorphic functions is okay. We know that F1z, F2z, they are meromorphic in between 0 and 1/2. Okay, they are holomorphic in between. And this follows from gamma x times gamma 1 minus x equals pi sine pi over x. So where x is in between 0 and 1/2, okay, then we are done with the first part. You have a meromorphic function well defined on C. We still denote it by gamma z. Then second step, try to locate the poles. So for this part, noted that gamma z so for real part z greater than -1, gamma z is defined by gamma z plus 1 divided by z. And similarly, for gamma z greater than -n, gamma z is defined by gamma z plus n divided by z times z plus 1, z plus n plus 1, minus 1, sorry. Okay, then this means because gamma is holomorphic, so notice that the argument here z plus 1 is real part of z plus 1 is greater than 0. Real part of z plus n is greater than 0. So that's the original definition through the integral representation, which is holomorphic for sure. And then this means that the poles of gamma is contained in the subset, in the set 0, -1, -2. And all the poles are simple poles. Okay, then next you need to show that those poles do occur in the question. Z equals 0, -1, -2 are poles of gamma z. So above argument only tells you the poles are contained in the non-positive integers, but they didn't tell you there's a pole at that point, because gamma z plus 1 over z probably cancel out with z if gamma z plus 1 has a factor of z. Okay, that's possible. So you need to conclude this. So how to show this? This is because look at the function. The gamma function pi over sine pi over z. Now this is for all complex numbers except possible poles. And now near poles you will see at each point z equals 0, -1, -2. Then what do you have? Then you have that the right hand side is singular because it's pi over 0, and then left hand side must be singular as well. But gamma 1 minus z is holomorphic function. Therefore, gamma z has a pole at those numbers. So then we complete the proof and precisely locate the poles of gamma function. Okay, now let's turn back to the beta function. So next we use integral representation to represent the duplication formula for beta function and the gamma functions. This formula, I think it's known very, very long time ago, probably before Euler. And later on, people also find a similar formula. Probably before that, find a similar formula for elliptic integrals. And then that corresponding to the addition on the torus. So that's a very important feature of the number theory. Most part of number theory deal with elliptic curves. Elliptic curve just a torus from topology. And on torus, how do you define addition? So that is related to the addition formula of the elliptic integral. So here, we just use some elementary method to show one of the relation. From 0 to 1, d lambda divided by lambda 1 minus lambda. Okay, then suppose you have this integral, then naive way is we try to evaluate by setting lambda equals sine square. Then what do you have? Then theta is from 0 to pi over 2 d sine square theta divided by square root sine square cosine square d theta. So that will be 2 sine theta cosine theta sine theta cosine theta 0 to pi over 2 d theta. So it's pi. And then you have gamma. Now let's determine the gamma 1/2. So this will be pi. Therefore, gamma 1/2 is square root of pi. Okay, next, let lambda equals 1/2 minus. You will see why we take 1/2 minus 1/2 square to u later. Then lambda times 1 minus lambda is 1/4 minus 1/4 mu. D lambda is minus 1/4 d mu divided by square root mu. Therefore, beta xx is given by lambda x minus 1, 1 minus lambda x minus 1 d lambda. And you first, by the symmetry, you can, because x, here y is x, you have symmetry. And then you can split it into two parts. And you get this formula. The other part, integral, is the same as the integral from 1/2 to 1 is same as the integral from 0 to 1/2. Therefore, you have this formula. And then you use substitution introduced in the above, which gives you 1/2 integral from 0 to 1, 1/4 minus 1/4 mu, x minus 1 mu, negative 1/2 d mu. And if you simplify, you have 2, 1 minus 2x, integration 0, 1. So you see why we have a 1/2 kind of stuff here, because if you scaling it, 1/2 now becomes 0 to 1 again. And inside you have 1 minus mu, x minus 1 mu 1/2 d mu, which is b x 1/2. Okay, then what does that mean? That is gamma x divided by gamma 2x is 2, 1 minus 2x, gamma x, gamma 1/2, gamma x plus 1/2. Okay, then you plug in all the known results. So gamma 2x is 2x minus 1 divided by square root of pi, gamma x plus 1/2, gamma x. So this is kind of a duplication formula, addition formula, that if you have two gamma times together, and you can just meld them together to a single gamma function. yeah, this is very significant, and when we talk, if we have time to talk about elliptic functions, we will come back to this again. Okay, next we end up with this topic by the following application of residual theorem computation. Before we only talk about the integral. Now we will see that actually we can compute sums in a similar way. Partial fraction, expansion, meromorphic functions. And due to time, I will only introduce the main idea. If we have time, we can come back. Okay, also I want to say the residual theorem and the contour integral is very, very important in analytic number theory. Because in analytic number theory, how to connect the analytic tool to the discrete prime numbers. So from the residual theorem, you see it's a natural way to use this theorem because the residual part is always discrete and that part is integral. So if you have good integral or the appropriate contour integral or some function, then you have a good estimate for the prime number set. Okay, for the detailed proof for some basic things, just like prime numbers here, probably we will start the setup, but I don't know if we have time to finish everything. But it's on your textbook. If you have interest, you can read that and choose that as your reading topic. Okay, so now the question is, we want to sum this up where PQ polynomials degree Q greater than degree P plus 2 and Qn is different from 0. Otherwise, it's meaningless. So idea is find a meromorphic function fz on C whose poles include z equals n for all the positive all the integers and use a sequence of contours Cn with the property that the domain enclosed by Cn is increasing as n goes to infinity and approach the whole domain C. In other words, exhaust C and limit integration of Fc dc along Cn is 0 and the residues of Fz at z equals n is Pn divided by Qn. Then the summation is transformed. Actually, it's transformed by integral by parts. If you really have in your mind the proof of the residual theorem. So A J is in C. AJ is different from N residue AJ. Z equals AJ FZ. So in other words, the summation of residue is 0. Okay, then the residue at the point N should equal the residue in the remaining places. So we have several choices. So first choice, we times pi cotangent pi over z. And the reason is pi cotangent pi over z is cosine pi over z times pi sine pi over z has a simple pole at z equals n. Okay, then also limit pi z minus n divided by pi sine pi z cosine pi z is -1 to nth power divided by -1 to nth power pi z minus n sine pi z minus n. I'll take the limit. Which is 1. Therefore, then PZ QZ pi cotangent pi z has a simple pole at z equals n with residue Pn over Qn. Okay, now let's consider the contour. We need to control the boundary integral. You will see why we choose a square instead of a circle. So here is x equals -1/2, x equals 1/2, -1/2, 1/2 I, net 1/2, 1/2 I, -1/2, -1/2 I, 1/2, -1/2 I. Okay, so the outside vertex is n plus 1, n plus 1/2, n plus 1/2 I, n plus 1/2, n plus 1/2 negative I, negative n plus 1/2, n plus 1/2 I, negative n plus 1/2, negative n plus 1/2 I. Okay, then we claim pi cotangent pi z is bounded for z on the curve Cn. Uniformly bounded. Uniform means it's independent of the integer n. Then we are done. Why? If we have the claim, by the claim, the integration of Cn 1 over P z over Qz pi cotangent pi z dz is bounded by the integral Pz over Qz dz times some constant. Okay, now because of the degree assumption, degree Q is 2 greater than P, then this one goes to 0 as Sn goes to infinity. So that's why we need to bound pi cotangent pi z. So now let's prove the claim. So first notice that cotangent pi z absolute value is cotangent pi z minus 1. Therefore, it suffices to bound pi cotangent pi z on the stripe or the boundary of the stripe on real. So on the two parts, real part z equals 1/2, imaginary part z less than n plus 1/2, greater than minus n plus 1/2. This is the first part, and the second part, imaginary part z equals n plus 1/2, real part z less than 1/2. Okay, then also noted that when y is greater than 1/2, we know cotangent pi z is exponential I pi z plus exponential negative I pi z divided by exponential I pi z minus exponential negative I pi z. Take absolute value, and you can estimate this is less than exponential pi y plus 1 divided by exponential pi y minus 1, less than exponential pi over 2 plus 1 exponential pi over 2 plus a minus 1. So what does that mean? That means the max of z in Cn pi cosine pi z must be less than or equal to maximum imaginary z in 1/2, negative 1/2 to 1/2, real part z also in negative 1/2, pi cotangent pi z plus 2. So you can reduce the estimate finally to the box with length 1, center at 0. Okay, and so this is trivial because pi cotangent z is continuous on this region. Okay. Then we are done. So it must be bounded. Okay, I will stop here. So next time we will start a new chapter on the general property of holomorphic functions and the conformal mapping. Okay, I will stop here.